shape, but it's the same person. I'm a last year PhD student, so this year it will be tough because I need to deliver a thesis, but finger crossed. And this is my email. Please contact me if today or next week or whenever you will use this tutorial again, you have question. If you have question, just text me on my email. I asked you to copy this notebook on your Google Drive because today I tried to deliver a very code-oriented lesson. Okay? Today we will discover what is natural language processing. Probably you have already had some intuition in the previous days. Well, today we will see that this is not magic, or at least if it's magic, you can do on your own laptop, on your own notebook. So, let's start by a definition. What is natural language processing? Well, we can say that it is a branch of artificial intelligence that works with text, of course. There are other branches that work with images, with videos, etc. With natural language processing, we are analyzing only text. The lucky part is that we have a really enormous amount of text to analyze, so sometimes it's also useful to analyze something else, but in this lesson we will analyze text. So this is a branch of artificial intelligence that enables computer to understand, interpret, generate, and manipulate human language, that is text and speech. So the core idea is that today we will start from the simplest possible input, that is just a txt file, meaning raw text, okay? Well, we can read that kind of text, but computer cannot understand in the same way we do. So the job of today is to understand what the computer actually receives when we provide the text, and how we will transform this text step by step to make it easier for the computer to understand and to provide to the computer the instruments to understand and to manipulate this text and to analyze, of course. So the question that we should have in mind is what does it mean to read or to understand a text for a computer? Okay, this is something not intuitive at all. I mean, we understand text because we learn how to write and how to speak, and we do it in an unconscious way when we were very young. So how does computer learn? Well, we will come back to this question several times today, so just keep it, just pinpoint it somewhere in our mind. Let me describe a bit the workflow, just to calibrate the expectations. First of all, we will start in the first half of the morning. Let's see, I mean, I don't have expectations on the time, and please, if I'm going too fast or if I'm not clear, just stop me, just raise your hand, just ask questions. It's much easier if it's an interactive lesson, because I need to admit that it's the first time that I do a lesson for social scientists. So I need to calibrate my speech on the audience. And often computer scientists just stay silent, and in the end of the lesson they don't understand anything. I saw in the previous day, on Monday, that actually you work very well in class because you do questions. This is very good. Please do it also with me. And so, for today, we start with a first introduction in which we will read the text. We will pre-process it, meaning we will remove the noise. Actually, for us, it's not noise, but for computer, probably it is. We will see it very clearly. Then we will do a first representation of the text. What it means? Well, we will provide a computer what is inside the text only by counting words. inside the text. So in my speech, there are 36 word end. I don't know. We will see how to do some, how to plot this word frequency in order for us to be able to clearly see, to investigate what is inside our text. And probably here, a spoiler for later, probably here we will realize that just counting words doesn't work very well. And so we need something else. And we need to extend our explanation, our representation with TF-IDF. No spoiler, we will see later what it is. Then we will have a break. Hopefully it will coincide with the coffee break. Maybe not. Let's see. And then this is your turn, in which instead of just executing the code that I prepared, you will try to do what we already did in the tutorial on another dataset. So you will explore a new dataset. I don't think it's a difficult part, but I mean, questions are really welcomed. Probably the exercise is just to understand which part of the tutorial you need, copy it, just adapt a little bit, and apply to a new dataset. Then, after this practical part, we will go more deep into the details of some models that you can use to understand patterns of your data. Till here you were doing exploration. Now here we are trying to characterize the text with some models. We will see a very basic model to do document clustering. When you cluster documents, basically you are extracting topics from these documents, what they really talk about. We will do some linguistic analysis. And finally, in the last part, we will see how we can improve our representation of the text in order to provide to the computer not only the words that are in a sentence, but also the meaning of these words. So we will try to communicate to a computer the meaning of each word. I think this is the magical part. I studied this. I know how it works. Still, it's magic for me, so I hope it's magic also for you. So while we were talking about magic, well, I think maybe yesterday you downloaded some data, some text. If you feel confident, you can use this data, this text for the today lesson. But I calibrated this tutorial for this text. That is the first book it's a part of the first book of Harry Potter. It's not a casual choice. I chose this book because we are talking about magic, so what better of Hogwarts school to do that? If you decide to use a different text file, you may need to adapt some small parts. Maybe it's convenient for today if we all use this text here. But then when you are at home or for the projects, you just try to change the input and you see how you can analyze your document, your text through this tutorial. For this first part, we assume that the TXT file is stored in the same folder in which we use the notebook, and that is just a TXT file. You can find the link to the document here. Okay. Now, probably there is also a way to import it directly on your Colab from Google Drive. But since I'm skeptical about that, I will download it. And it's quite fast. And I will upload it here as soon as this stops to. Okay. So to upload the document, maybe you already know, you just need to go here, and then I will upload this one. Actually, I already have a copy, so I will. this is a warning telling you that these documents that you upload here are just in the cache so they are not saved they are just temporary. If you close the notebook or after lunch when we will resume, probably this document is not here anymore and we need to upload it again, okay? So, I will wait for you. Just tell me if you finish to upload the file here and then we can start. Okay? Raise your hand if you didn't finish. Okay, let's wait. No, raise your hand if you didn't finish. Okay, you finished. You didn't. Yeah, okay. Any problem?
It's uploading.
Ah, okay, cool. So, well, from the beginning, I will just spend time by talking. Just tell me when you finish, okay? Okay. So, first of all, here we will just define the path of your document. If your document is in the same folder of your notebook, and of course it is in Google Colab, you just need to write here the name of your document. Then here we will read this document. What is that? I don't remember if you see it in the previous days. Basically, with this line of code, we open a streaming in the same way you open your YouTube video, and we start reading it. When we are outside this block here, for example, the streaming is closed. Never mind, it's a technical detail. But even if the streaming is closed, we saved every line of our document in this list that I called lines, okay? What is this list lines? Well, it's a list in which every element of this list is a string, so a text, basically. And in particular, from our example, every element is a paragraph of the book, okay? So we can see an example here. This is the first line of this very famous book. Okay, here we use the read lines. That is a cool method to just import the text line by line. So it reads the file line by line. Each line becomes one element in a Python list. And basically how it defines lines. Well, basically it searches for this character. This character is the computer way to say carriage return. Okay? So for every carriage return, it takes a line. So it's very intuitive. How many lines do we have in this file? We can use the method len, and we see we have more than 6,500 lines. Now, this is very important, and computer scientists never do, and I'm very mad for this, okay? With my computer science student at Polytechnic. Please inspect your input. This is very important because every time you do something automatic with computer, something happens, and you need to check if the output of what you do is in line with your expectation. For example, if we print the first 5 lines of this book, we will see that actually there is something wrong. There is a line with text, then a line that is basically empty, then a line with text, then a line that is basically empty, and it's like that for all the text. Why? Well, because in this text, this is specifically of this document, they use to carriage return, so to/n, like this. To separate the lines. So read, you can say, okay, split in read lines, you can say, okay, use this as a separator of lines. Or you can use other method. I will show you another one just to be clear. And but well, the message that I want to deliver is every time today we do something, then inspect the result, because something happens and maybe I didn't want that. So sometimes we prefer to work with the entire text as one string and then to manipulate in the way we want. Depends on what you prefer. To do that, we open again the streaming and we read, in this way we read the entire text, okay? So here I'm printing the first 500 characters of the text. This is almost 2 paragraphs of the book. Now, once we have the full text, why I prefer to use this method? Because now we can ask to split the entire text into parts, into bunch of text, choosing the separator that we prefer. And this time I choose as a separator the double carriage return. And now the text looks well formatted, meaning every line it's at least has some text in it, so good enough, I would say. Well, even in this case, I will be boring, sorry. Always expect the result. Indeed, when I did for this tutorial, I discovered that at a certain point, you can find lines that are basically empty, where there is only an empty space, or lines that starts with a carriage return, like the line 8. So I don't want that, this is noisy. I will just remove them. But the message again is expect your data, because every time you work with the human produced data, sometimes also LLM produced data, you will find this kind of mistake, because the writer did something wrong and the editor didn't check it properly or whatever. So this is a very common situation in which we have, let's say, spaces that we don't want. Let's remove them with the method strip, dot strip. So given a sentence, we do, given a variable that is a string, it's called example in this case, we do example.strip. What changed? That here there was this space and this space, here there isn't. So it is well formatted. Once we do this, we can use this method to eliminate all that lines that are basically just empty spaces. Why? Because when we use the method strip, it removes these spaces, and then if you check your sentence, you just see an empty string. Okay? So in this for loop, we will just create a new list that is called clean sentences. Basically, how does it work? We do a loop on every line. Did you see the structure, like the for loop? Do you know how it works? Okay. So for every line, we use the method strip. This somehow clean the string. If the cleaned string is empty, we jump it. Otherwise, we append to a new list that is called clean sentences. That's it. And now we have, instead of 6,000 lines, now we have only 3,000 lines. Okay? Now, expecting your data, your corpus manually, it's boring. Sometimes it's better to use some quantitative analysis. A good way to do that is to plot the number of characters in every sentence. Because at least then you can check the codes of the distribution, and you can check the tails of the distribution, and you can check if long text are too long, so there is something wrong, and short text are too short, and there is something wrong in them. So here I'm just, for every clean sentence, I basically represent in this list how many characters there are in each sentence. It's the same logic of a for loop, except, can you see it? Is it too small? Please stop me, okay? Last row, can you see it?
Yes.
Okay. Sorry, ask me, please. So now here I was telling, we do a for loop and we create a list in which every element of this list is the number of characters inside the sentence. And now we use the library matplotlib to plot an histogram of this distribution. That's it. What we see? We see that a lot of lines has the large majority of the lines has less than 200 characters. There are few lines that are very, very long, 1000 characters, and some lines, not a negligible part, that has less than 10 characters. Okay?
Is that possible?
Huh?
Like 1,000 characters? Is that really possible? Or is there some kind
Seems to be long, right? Well, let's...
Because it's not taking sentences, it's taking lines, and lines are made up of different sentences as much as
yeah, it's here by my decision we are taking paragraphs.
paragraphs. Yeah.
So, can be a very long paragraph. It's not the best choice, we can debate about it, okay? But when we do this, I will deliver this message later, but whenever you do this stuff, you need to explain why you take some decision. In my case, I decided to analyze paragraphs. It was easier to do that. This is the reason why I choose this.
what if I wanted to do words?
Words?
Or sentences, yeah.
Well, for words it's quite easy because you call the method split, and you say, okay, for every space does a split, and then you have every single word. For sentences can be a bit more difficult because you need to split on something else, for example on dots. But if I split on dots, I have some sentences as the first one, for example, in which there are some dots here. How we do that? Well, actually, we need to manipulate a bit more our text, like, for example, first of all, searching for these patterns. There is no way that we can really catch this pattern. There is just a mistake here, there is a space here, so never mind, we will consider it as noise. But for example, for these misses, we can at first catch this pattern, remove this dot here, and then split the text into sentences, okay?
We can say ChatGPT like divide this text into statements without using dots besides at the end of the statement.
You can ask Gemini or ChatGPT to provide a code to do that. You can also ask to provide just to split.
But at least adjusting the statements as it was, there is no dot in the middle of the
No, for sure it works, so you can do it, but sometimes the texts are too long to pass to ChatGPT. Here we are analyzing only one book, and I say only one book. How many hours you need to read one book? Probably, at least a day for me. I don't know, this is a small book, but imagine that you want to analyze a library, all the books of the library. I want to provide you the code to analyze all the text, not just an example, okay? So the best way is to ask our AI assistant to provide the code to do that. Since we are at the beginning of this class, please accept the fact that this time we will work with paragraph. I will show you later some methods that you can use, for example, to substitute the part that you don't like with something else and then to split the sentences. But since it's a bit premature now, we will use only paragraph for the entire day. But when you have your work, you can decide. And this is, yeah.
Sorry, I wanted to know whether if we're working, for example, with comments on social media,
Yeah.
can I, rather than working with lines or paragraphs, work with comments?
Yeah, this is an excellent example. In social media, you have comments. Every comment is a separate document. You don't want to split them, so you use just the comment. I usually work with comments. I usually work with social media. So, in my case, I usually work with Telegram. So sometimes I use every single message of Telegram as a different document. Sometimes I use the entire chat as a unique document. Really depends on your choice. And you just need to motivate in your paper when you write. You say, I wanted to use document. I want to use comments as documents. That's it. It's just need to explain that. So where we were, I lost that. Okay, we did this plot. Also, there are very long paragraphs and very short paragraphs. Let's print them. We see that long paragraphs are quite boring. Here what I'm doing, I'm printing all the lines that have more than 600 characters and all the lines that has less than 10 characters. For the long paragraphs, they are long, but they seem to be right, so never mind, we will keep them. For the short one, instead, we see that they don't deliver enough content, and sometimes it's just a noisy content. Okay, yeah, imagine to have a paragraph like this. It's not reliable, right? So we will remove them from our list because we say, okay, this does not deliver enough text. It's just noise, and so we will skip them. So once again, we create a new list in which we do a for loop on the previous list, and every time the sentence has less character than the one that I choose as a threshold, I choose 10, I could choose 100, no one will arrest me, but I need to explain why I choose 10. And that's it, we create a new list. Now, we have a first step of preprocessing somehow, but computer scientist doesn't like to call this preprocessing because we call the next step preprocess the text. When we preprocess the text, basically we start to manipulate the text again to reduce the complexity of the text. Because as humans, we are already able to understand a lot of complexity, but the computers are not so smart as we believe. So we need to simplify the text if it was for a child, let's say. And so we put our book, but this can be a book, this can be an entire library. We do some trick to manipulate the text, and then we have the preprocessed text. The preprocessed text is something that is quite difficult for us to read because we prefer the complex way because it delivers a lot of content, but it's quite easy for the machine to understand. Okay. So the guiding question for this part is, what is information in a text and what is noise? I would say that probably nothing is noise in a text, but for computer probably it's easier to simplify stuff. So we are going to modify the raw text, and this is an important part. Preprocessing means to modify your text, so it implies that you need to do some choices. And so the preprocessing is not neutral. For every decision we make, this changes the representation of the text. It emphasizes some aspect, it downplays other aspect. For this reason, every decision that you do with preprocessing should always be explicit in your paper and motivated by research goals. Okay? I will do something standard today that everyone accepts because we know that computer works better in this aspect. But sometimes you can say, oh, I don't want this in my text. I will show you an example in which I will do something that I can do with English, but if I was working with Turkish, I couldn't do. And you should tell me, oh, if you are reading my paper, I'm doing this pipeline with a Turkish text, you should tell me, oh, no, Giordano, this is a mistake. You couldn't do that. We will see it later. So let's print our filtered sentence. Okay. Now, first thing that we can do, the easiest, probably the first that came in our mind, lowercasing, meaning to write the text in lower text. Why? Well, because this reduces the complexity, of course. The way to do it is pretty easy. For every sentence, we call the method lower, and that's it. So now every sentence is lower cases. Why we do that? Because we want to treat the word text with capital, or maybe I could choose a better example. We want to use the word example as the same word if it has the capital letter or if it hasn't, okay? If it's at the beginning of the sentence, it's capitalized, but in the end it's the same word, right? So this reduces the unnecessary variation because we understand that example is the same word if we use at the beginning of the sentence or if we use in the middle. However, it also removes some information. Example, we lose information on the proper names because my name is Giordano, maybe it's just a name, so even if you don't see it capitalized, you understand that it's a name. But sometimes, no, I mean, there are names that can be also the word for something else.
Hunter.
For example. Yeah, thank you. Again, this is a choice, not a rule, but seems to be quite fair to do that. What we see here are good practices, but always keep in mind to understand what's going on and why you are doing this stuff, because you need to understand why you are doing this to explain then to the reader of your paper. So, I can say that probably also punctuation can be noisy for a computer. Of course, it's not noise for us. We need punctuation to read the text. But maybe for a computer, at least if we use simple methods as in the lesson of today, punctuation can be just noise. So I will remove them. Tomorrow, with Yanni, if you will use LLMs, probably you don't need to remove punctuation because the models are so big that they can easily understand even the punctuation and even much more complex stuff. But for the models that we use today, they are quite simple, so we need to remove them.
Punctuation changes the meaning of the text.
Totally, yeah. But we are saying, I mean, the first half of the lesson is just counting words, no? And so if you count words, you don't need the punctuation. But of course, we need to keep in mind that we adapt the preprocessing to the methods that we are going to use later. Because if I pass the text to an LLM, so to Gemini, I prefer to have dots because they change the meaning, okay? So, to do that, we will use this library that stands for regular expression. It's already installed on Python on the basic version. So what it does, basically these regular expressions describe a pattern that I want to find in the text. When it matches that pattern, you decide what to do. You want maybe to remove that pattern, or you want to just keep that specific characters and remove all the rest. We will see some example of these regex. So this is our example. In 2024, visit example.com website for more info. And then I tag the user 1213. If I remove numbers and other characters than letters, I will obtain this. In visit, this is more difficult to understand, right? But it's easier for a computer. So this is an example of a regular expression. It's a compact way to tell the computer which characters or patterns we want to keep or to remove. If I wanted to keep numbers, I should use this other regular expression. However, probably the real good computer scientist knows how to write a regular expression. I don't. I always ask ChatGPT to provide me the right regular expression. It's trial and error, because maybe sometimes ChatGPT give me a regular expression that is not what really match my question. So I try on my text, and then I return to ChatGPT. I say, oh, you made a mistake because I want this, etc., etc. Trial and error. So this is a modeling choice. We are not simply cleaning the text. We are deciding what information is relevant and what information can be discarded. For example, numbers in this example. Different research question may require different rules. For example, for someone of you, proper names are really important and you want to keep them. So maybe in that case you don't want to lowercase your text. A standard procedure is that, especially if you work with social media data that are very, very noisy compared to a book, because no one edited them, before removing punctuation, it's a good idea to remove specific patterns like URLs and user tag. Okay? So to remove URLs like HTTP or www. something, we just use this regex. I don't really know how it works, how to write it, so I just keep it, and you also should. Yeah.
If I'm dealing with comments
Mm-hmm.
and posts, for example,
Yeah.
should I tell the program to remove pictures and emojis, for example?
I will show you just in 2 blocks how to remove emojis. For images, instead, here we are thinking that we have only text. Okay. Because also on social media, probably they are in different field. Let's imagine that you just copied the text of the post. Okay. So here I'm removing the URLs. The URL now is gone. Now I want also to remove all the words that starts with the @ because on social media we use the @ to tag someone, and we don't want to use the name of this someone on our example. So we will use another specific regex for that. As simple as that. Let me show better. We are saying, using the library use the method sub, that stands for substitution. When you find this pattern, substitute with another stuff. This time I'm substituting with an empty string. Maybe here I want to substitute with the letter, with something like this. And now, instead of the tag, you have a word that is called tag. Okay, so really depends on you. Other things you may want to change and this comes to your question, we want to replace emoji. To do that, we use the library emoji. Sometimes we want to transform the text to have only ASCII characters, okay? We will use to do that the UniDecode library.
What are ASCII characters?
Yeah, what's that?
Good question. Let's say the standard English characters. Like, is it a good definition? I mean, reasonable. Yeah, maybe you know the answer better than me. So, if you have another answer,
I would say just let like the English alphabet, the numbers, and the punctuation.
that's it. Okay.
No accents, no weird symbols, like non-American characters.
Let me do this example. If you use, if you are writing in Turkish, probably there are,
Many small characters.
yeah, there are characters that are not in the ASCII standard. Okay? So, this is the point in which you shall tell me, oh, you are Giordano analyzing a Turkish text, so you don't need to use the UniDecode library because you are transforming the meaning of our text. If I'm using Turkish, I want to work with Turkish, of course. In my case, I'm analyzing an English book, so I can pretend to transform everything in UniDecode, okay? Yeah.
In this case, this brings me to another language, which is Arabic. I work with Arabic, so does this also apply, the cleaning, etc., to another completely different language, which is like Arabic?
Whatever we said so far, yes, except for the UniDecode, probably. Because Arabic is not in the ASCII standard, I'm sure that there will be library to properly process and standardize the Arabic text. Unfortunately, I don't know because I never worked with Arabic, but it can be, I mean, this works specifically for English text, but I encourage everyone here to work with other kind of text just because everyone only work with English because English it's easy. There are already a lot of people that work with it, so we already know the good practice, etc. But recently in conferences I saw much more paper that try to deal with other languages, Chinese, Arabic, Turkish, other than. Us as Italian, we are facilitated because we use also the ASCII character. So, other idea can be to remove non-alphabetical symbols. Again, non-alphabetical for English alphabet, okay? We want sometimes to remove extra spaces. So if we have two consecutive spaces, we want to keep one, the other is noise. Or maybe we want to remove from our text all the words that have one character or two character or three character, etc. Depends how long you will write here. Here I'm telling to the string, remove all substitute every word that has one or two character with an empty string. Okay? Again, I'm telling the computer that is noise. It's not noise. It works for us. But we are trying to simplify stuff for the computer. Why? Because probably the words with one character or two character are just stop words. We will see later what is a stop word, but basically it's just a common word that does not deliver the meaning in a specific context. Let's think to the article de. The article de can be used in every text, doesn't deliver a real meaning of, for example, the topic, and so I will say, oh, this is noise. It is not, but for computer it. Okay, so let's return on working on code. We install these two libraries. To install libraries from your notebook, you just need to use this, how is it called, this marker? The exclamative dot? Exclamation mark, thank you. I'm sorry. So we install the library emoji, we install the library Unidecode. Okay. Now, once we finish to install this library, we will do, for every sentence, we will do all the steps that I mentioned before. So, we will remove URLs from our text. Of course, I don't expect to have URLs in the Harry Potter book, but maybe if I'm working with comments, there are URLs, and I'm pretty sure that there are URLs in comments. We want to remove tags. We want to remove emojis. We want to standardize the text to the ASCII style. We want to remove numbers. I don't know if there are numbers in Harry Potter book. I don't remember. Let's remove them. We remove words that have only 1 or 2 characters. We remove empty spaces. I mean, we remove double spaces substituting with only 1 space. I already did that before, but I will also avoid strings that have less than 10 characters while I'm doing this again now. Because once I did all this manipulation, imagine a comments that have only an URL. Now that I remove the URL, now the string is empty, and so now I need to filter it out. Okay? So it's a good practice to filter sentences or documents or comments before preprocessing, but also after preprocessing. Okay?
What if the comments, for example, for a platform where young people participate, they use less words and more emojis? So if I remove the emojis, I'm left with very little text.
Yeah, totally agree. And because it's not the standard emoji, but is the...
I just leave them, yeah.
Yeah, maybe yes. Depends on the model that you are using. Maybe it's a good idea to do a back of word, and instead of words you use emojis. So you include emojis into the words that you want to analyze.
Who transform emojis into words?
Yeah, somehow, no? Yeah, I mean, it's in the end it's a word. We don't perceive it as a word, but it's an expression. It's a symbol, so can be interpreted a word in a extended meaning. I have a question from there.
I was building on this, like, if we do sentiment analysis, emojis are important. Emojis can be important for sentiment analysis.
Yeah, totally.
So,
I agree.
So is there a way to navigate that?
Depends on the model you're using. Again, if you're using LLMs, they are so powerful that they can deal with everything. Because maybe I say something ironically, and then I put emojis, and then if I remove emojis, people can't understand that I was ironic. Yeah, this is quite a big problem to understand irony. I mean, computers are not very good in understanding them. Maybe LLMs are, but previous models are not. There are a lot of computer scientists that did a PhD in trying to explain irony to models. This is specifically difficult for some kind of languages, for example, for Russian. I don't talk Russian, but as far as I know, it's quite... Okay. There is a lot of ironical sentences in Russian speech, and it's also difficult for us, like sometimes if I need to deal with Russian comments, I translate them, but translating maybe I lose the irony. And so this is an open point, of course. By the way, in this case, let's consider that we can remove emojis. It's okay to remove them if I want to, for example, understand the topic of discussion. If instead I want to characterize how this, if instead emojis are important for us, I should try different approaches, like counting also emojis together with words. So now we will do a last step of preprocessing. I don't know if I finished to do that. Yeah? No? Yeah. That is called lemmatization. I'm not familiar with linguistics, so if I say something wrong, please correct me. Lemmatization basically consists in the process of reducing the word in its root form to reduce again noise, variety, because we want to work with simple word, because the complex word is difficult to handle. So changing, changed, change, in the end they come from the same word, they somehow deliver the same meaning, so we reduce all these words in the same root form, okay? So this is something more impactful on our text, because now we are doing word variation. So again, before doing that, let's consider if it's good for our case of study. In my case of study, seems to be reasonable, so it will reduce run, runs, running, model, analysis with the American way to write it, or analysis in the same root form. In this way, we treat different form as the same word. And
even plural and singular.
Yeah, this is, I mean, we can debate that is not the best things to do.
You end up with a very poor text.
Yeah, but because the hypothesis there is that if you remove this kind of variation, the things that last, you may emerge the bigger things by removing the specific variation. Yeah?
You mean the essence of the text?
Yeah, not of the specific text, but of the groups of text, let's say. And it really depends on what you want to do. But imagine that I want to discover topics in a text. I'm always say I want to discover topics because a lot of time I want to search topics in my data, but some other people can work on different tasks. Well, in that case, you say, okay, if I remove running with run and plural with singular, etc., in the end, the topic is the same. We don't vary it. So, fair enough. Well, important notes. Lemmatization uses linguistic information. So, this is also the case, like the verb to be, I am, you are, everything is transformed in be, okay? So there is a strong variation of the text. But we accept that because we just want the verb to be. We want to know that in that sentence they use the verb to be. This lemmatization depends on the language. This is a strong remark. The quality of the linguistic model, but the models we are using now are quite powerful, and the domain of the text. Again, we pretend to use the same model in every context, but maybe, and always try to search for them, there are a specific model for your specific context. I'm a gaming person, and so if I analyze a gaming chat, maybe you want to have specific models that understand that some kind of language. For example, in Italian, I imagine in all the words, we use English words, but in an Italian fashion. Like, I will tell you in Italian, ho killato, that means literally I kill someone, but in the games, okay? But you use kill as if it was an Italian verb. So, if I want to deal with comments in a gaming chat from Italians, maybe I should try to find the right model to use. If there isn't, I will use a general one, but I accept that probably it does not really understand all the context I want. Okay, so now this will take less than a minute, but it will be a bit longer. We use the library Spacie, and we will use the English dictionary, basically. These other stuff tell you the data they use to train this specific model. They usually use like whole Wikipedia, whole the web, so very huge corpus to train automatically these models. And let's see the effect. Okay, I removed the Mr. before. Now it start to be very difficult to understand the text. Like be proud instead of are proud. Maybe I can put also the original sentence. It didn't like, but I don't know why. It was an easy one. Okay, so this was the original sentence with very before lemmatization, and then there is the modified one. As you see, we lose a lot of variety in our text. So this is not a free choice. I mean, not meaning. Your choice has the impact of modifying the text. You are accepting that you are reducing the variety, okay? By the way, when lemmatization is too slow, because now we are analyzing only one book, but imagine that you want to analyze all the books of this university together, then we can do that. It's not that much text to analyze. We can do stemming instead of lemmatization. This is the computer scientist way to do stuff. Basically, instead of finding the word in the linguistic pattern, we just cut the sentence. So instead of run, we cut and we take the first split that is run. It works quite well and it scales very well, but sometimes you can't just cut word, you obtain something that is not a word. However, we don't care because we say, okay, but I'm analyzing all the books in this university, so it's okay to have some mistake in it. It's we accept to don't be perfect. This is, as you may see, it's much faster than before. Question? No?
I mean, can we not do lemmatization with the text? For example, problem, it does change somehow the syntax of the text sometimes. For example, if I'm looking at sentences, for example, one of the sentences, if I am in the original corpus is like, which is active sentence. Israeli forces killed 3 civilians. This is an active sentence which is attributing the action to the Israeli forces. And at the same time, like, I have a passive sentence.
I totally agree.
In the original corpus, which is like 3 civilians were killed in the operation. Here I can totally understand by reading the original text, like it is not attributed, the action is attributed not to the actor here. So the subject is absent here. But if I lematize the text, these same 2 sentences, what I get is like, Israeli forces killed 3 civilians. In this, like, I understand. In the second sentence, what I get is 3 civilians be killed in the operation. So it somehow also changes the syntax of the sentences, and I am not able to analyze like the moral distancing that.
This is a perfect example in which you don't need to do lemmatization. I totally agree with you. Motivate why you are not doing that, and it's fine. It's everything I'm showing, it's optional. I will not be there by looking at your code when you will do your research. Other question? Yeah.
The question is that if you don't do lemmatization, would the model still be able to analyze the text when we ask?
There isn't an answer to that. Just try. If you see that the model are not good enough, or you change the model, or you simplify the input, okay? And maybe I used some models in the past, so I have some expectation on them, but there are tons of models, so just try. So we saw that stemming is much faster. So this can be also good for you in your case. This time, by cutting the words, we are not removing if the sentence is active or passive. So maybe this can work better with you. Now, another thing. This is specifically, I think many of you can be interested in it. What if I'm working with Turkish text? Well, if I'm doing that, here I'm used an English model. I can't use it on Turkish text because it will do something wrong. So I basically download from Hugging Face. I will show you later what is Hugging Face. The specific model to work with the Turkish language, so to do lemmatization with Turkish language. Now, okay, it will take a minute. I just spoiled the result. So I import it. I use it. Now you should tell me. I did the lemmatization with the Turkish model, and I did the lemmatization with the English model. I'm not able to speak Turkish, so tell me, is this lemmatization better than this other one?
Can you scroll?
Yeah, of course. Sorry. It's a long question.
The second one is better.
The?
Second one.
The second one?
It's understandable, but it's not lemmatized really. The first one.
But so it's not lemmatized?
Yeah.
Okay. Well, here we accept to lose the meaning of the sentence because we are transforming it. We prefer to have something that is more lemmatized, but that is lemmatized correctly. Like verb I am must be transformed in I be, for example, using the infinite form of the verb.
Yeah, so in the first one we have the infinite and it's not understandable.
So this is why this should be better in our case, because it's doing what is designed to do, lemmatization. In this case, if I use the wrong model, this was the English one. It never saw Turkish, so it tried to do something, but it's not what we wanted. Okay. I will almost stop here. Then we will see word clouds, bag of words and word clouds. So we start to do a representation of this text. So far, we just manipulated the text, but we never provide to the computer a representation of this text. So the computer just did what we asked, but never tried to understand the meaning or something about the text. I just want to do a digression that you will see tomorrow, more in detail. I said, I will download the Turkish model on Hugging Face. What is Hugging Face? Actually, it's a very cool website in which there are in which there are a lot of cool models. Here I found the one for Turkish, but too big. I can't find the, okay. If you go on models, here you can find all the models that are on that are on Hugging Face. All the open models. So the models that you download and you can use for free if you have enough resources. Why I'm showing you this? Because, for example, if I specify the task, in our case, task can be text classification, for example. I want to classify the text to do, for example, sentiment analysis. So I choose the task. I can also choose the languages I want to use. Let's say Italian and Turkish as well. Okay.
Do you have Arabic?
Huh?
Do you have Arabic? Yes.
Of course. I don't know which model will work with Arabic, by the way, but
Look at all the flavors. Go back to typing Arabic. Look at all the flavors of Arabic you have.
Yeah.
okay.
Tunisian Arabic.
I mean, this is just a filter. So maybe when you put the filter, then you finish with only few models, okay? But however, let's accept that we never mind. What I wanted to show, I lost the sign, but what I wanted to show is that maybe you want to do sentiment analysis on Turkish. Well, there is already a model to do that does sentiment analysis not only for Turkish but for a lot of languages. Someone already trained for you this model, so you don't need to implement things from scratch. You will see something about what is inside this model, but tomorrow. The good part is that I don't need to know what is inside. I just need to know that it works and that someone already trained for me. Here somewhere you can have the languages that it accepts. By the way, I just wanted to show that I installed the model here. Where is it? I will not do it now because it takes a bit of time to download the model. But basically, I use this library. I don't need it to write this code. There was directly an example here in Hugging Face. I imported the model. This is an example. Oh, sorry. This is an example sentences. I input this in the model, and I have results. The results is that this sentence is very positive. If I'm doing sentiment analysis, is what I need. So now I can use this model to provide the sentiment to every paragraph in my text. And here I just took a bunch of these of the words in our text, and here I wanted to split the most negative, the most very negative, the most negative, the most neutral, the most positive, and the most very positive. Why I'm saying the most neutral? How can you be the most neutral? Means that the model classified the sentence as neutral, and every time it made the classification, it also provided a score. I'm taking the sentence with the highest score because the highest scores mean highest confidence of the model to provide this label. Okay, that's it. So in just the time to download the model and a few lines of code, I'm able to do sentiment analysis without just knowing a few of Python and no information about this model works inside. Okay?
I have a question. If you install a package within the terminal and this file and you install and import whatever libraries, next time you open a new file, a new project, do you have to install the same package again, or that would already be installed?
Well, thanks for the question. I needed to tell at the beginning and I forget, so thank you. For Google Colab, yes, because Google Colab does not have a memory. Okay, it's just temporary. They basically borrow you some memory. If you are inactive, they delete everything, and so you need to install again. If instead you are working on your laptop, on local files, once you installed, it is somewhere on your laptop, and the next time you just need to import without downloading it again. Okay, this is why I don't really like to use Google Colab, but depends on what you need to do. I need to work with a huge model for a lot of time, so I don't want any time to download the same model again, so I'm working locally. Use the Jupyter Notebook? No. By the way, it's the same interface, but locally on your computer.
And without Gemini.
And with
That's the thing.
yeah, there are also ways actually to have Gemini on it. Like if you, not Gemini, but if you use Visual Studio Code, that is just an editor, you can have something assisting you. We didn't show you this because it takes time to install, to set, to have everything down, and then sometimes libraries does not work as you expect. Instead here you just need to plug and play. So it's much easier to use Colab, but you can use also your local model. Other questions? Yeah.
This is sentiment analysis for formed outputs, right?
Yeah.
It says, for example, I was reading through the outputs and it says, none, they noticed large tawny owl flutter past the window. So a bird flutters past the window. Label negative.
Yeah, there are a lot of things that are labeled
And then they
negative.
say like, someone leaves the house and gets into his car, negative.
Leaves. Yeah. It's a negative.
I don't know. I mean, models are not perfect in any way. We really expect that at least the large majority of the answers are right, but we always need to to validate our model. So, what my mistake here is that I should annotate a bunch of sentences. And then I should try if the model works and if it provides the same label that I give. Not me specifically, but maybe let's imagine that 3 of us independently annotate the sentences and then we check the performances of the model. In this way, you know if your model works in your context. Maybe here for a Harry Potter book, there are not very strong negative sentences so it will make some mistakes. And yeah, my error here is that actually there is also another problem. I just provide 100 examples just because I want it to be fast. And so in 100 examples, maybe there are not really negative sentences. If you do on the whole book, maybe you find something more negative.
May I ask, like, since I'm so unfamiliar with this, like, is sentiment, like, this, just from this small example set, my feeling was like sentiment analysis was developed more for companies or financial transactions where something is like really starkly positive or negative.
It can be, of course. We really work with social media data when we do sentiment, so we want to feel the taste of the conversation to understand if they are negative or positive to something. We want to discover patterns because maybe sentiment gives you information about how a community is about some topic. Also, sentiments is not the only thing to watch. For example, I usually do, instead of sentiment analysis, I do stance detection because I can be positive or negative against or pro someone, but I don't want to understand the sentiment, but what is my stance, like let's talk about guns in US, okay? I can say a sentence like, I'm so afraid that that I can't defend my house if someone arrives to. Guns. So, stance is different from sentiment. Yeah. I hope you didn't fall asleep yet, and let's have a break now. Okay. Okay, here we are. I will start because we have so many things to do that we must run a little bit, okay? But please stop me every time you need, okay? There are no dummy questions, okay? And actually it's very important to ask questions. So now we are doing a step further. So far we manipulate the text. It's fine, but yet the computer doesn't have a way to represent our text. What it means to represent a text? Well, computer doesn't work with words. They work with numbers. So now we need to transform our text into numbers. And there are several ways to do that. We will start from the easiest one, and then we will increase the level of complexity. So, the first way that we can do to represent a text for a computer is to count the words that are in the text. This method is called bag of words, meaning you do the bag of the words in your text. So here you have a text, and you start to count how many times the word it appears in our text, how many times the word sweet appear in our text, and so on. And so you basically, this list of numbers is the representation of this sentence for your computer. Okay? Now, first of all, why it's important to pre-process the text before? Because the bigger the vocabulary, the bigger your bag of words. So if it's bigger, it's heavier. And so maybe if it's too much heavy, it cannot fit on your computer. So you need maybe more power to do that. And also, there is a problem in machine learning that is called curse of dimensionality. You don't really need to know about that, but it's basically tells us that the more dimension you put, the more the complexity, the more ineffective becomes your models. For example, if you have much more dimensions, much more words, it's more difficult to do, for example, classification. So we try to compress the complexity to have something simpler. Sometimes this is not acceptable, sometimes it is, depends on your case study. In our case study, so we start to count words. This is the simplest way to represent the text. And so we will provide to the computer a list of documents. I will call documents every element in the list. So in our case, a document is a paragraph. In other cases, a document is a comment. Okay? And we will use the class count vectorizer to make this. So we don't write the code to count the words. We just borrow the library from someone else. So let's see. In our list now we have slightly less than 3,000 documents. And this is the classic example of one sentence in our list. It has been lemmatized, so now it's more difficult for us to read and understand. We lose a bit the meaning, but it's okay for the computer. So let's import count vectorizer from, this is the name of the library. This, you can see it as the subsection of the library. Okay, let's consider this as a library. That is the book that we need. That is the section of the book that we need. And actually we need only this object, count vectorizer. Yeah.
What does vectorizer do? Does it put it in a context?
Sorry?
What does vectorizer do?
Just count words in your sentences. So, if I say the sentence, fit the vocabulary and transform the documents into a count matrix, we'll say fit appears once, the appears twice, once here and once there. Vocabulary appears one. We just do that.
So, I mean, do we really shove all these words into the bag without any caring for the order?
Yeah, this is a very interesting question. I will answer that later in the afternoon. But yeah, we are losing the context of where this word is used. Okay? Because we are starting from doing the simplest stuff. Then, especially tomorrow, we will see that we can do much, much more complex stuff. But at the beginning of computer science, some years ago, before 2017, we can do basically only counting words without the context. In 2017, we discovered transformers. Transformers changed our world. It's the brick that allows us to arrive to LLMs. You will see a bit of that tomorrow. Today, we just count words, no matter of the context they are used in. Okay? So, I will not explain the detail of the code, but this is basically you create this variable that is your count vectorizer. This is actually an object, but too much details. You fit transform your sentences. This method fit transforms create a matrix that I called xbow. What is a matrix? A table. Okay? N rows, M columns, just a table. In this table, this is a compressed table, a compressed matrix. Why we use compressed matrix? It does not really matter, but, well, in every sentence that we say, we use just few words compared to the whole dictionary, right? Or to the all the words that they are used in the book. And so there will be a lot of zero. We remove the zero, we only count when there is a number in it. But this is a technical stuff. We use this stuff to save memory, basically. Just consider this. So this is a matrix as a table. This matrix has 997 lines, rows, and more than 5,000 columns. Every column corresponds to a word. And in the intersection of the column and of the row, you have how many times the word has been used in the sentence. Okay? Now, sometimes you want to do something more complex because actually complexity is good. We are always trying to simplify stuff, but complexity is good. What we can do, for example, instead of only using simple words, we can use bigrams. So, couples of two words. By doing that, we are maybe a couple of words are more important, like in this case, maybe Harry Potter as a bigram is quite important, as Harry by itself. I mean, Harry Potter is a bigram, very important in our representation. By the way, in the example that I'm doing now, I'm just counting single words, okay? And it's enough for what we are doing now. So I fit my matrix. Let's do an example, just to show you the difference. If we count words, we have the words in the example, the cat eat the mouse. We have the cat eat the mouse. 5 words. If we use bigrams, we have the cat eat the mouse. So we have 1, 2, 3, 4 bigrams. If we use both of them, both single words and bigrams, our dictionary will have both this information and this other information. So we'll count for the single words and for the bigrams. Now, we want to inspect the result. We have in this table, in this matrix, I will use the word matrix, but now you know that it's a table, basically. Every row is a document, so the representation of your sentence, in our case of our paragraph. The column, every column corresponds to a different word, and the value inside the matrix is the count how many times that word appears in your document.
May I ask something?
Yeah.
What kind of difference it would make whether we use
Bigram.
diagrams and unigrams? What, in terms of analysis, and how that distinction would make difference when we are looking at the numbers identified by unigrams and the numbers identified by bigrams.
We are providing to the model a way to understand a little bit of context of where this word has been used. So here cat is just cat. Here the context is cat hit. So you have a noun and a verb. So we are just improving the context. This can be useful, for example, Yanni before was doing the example of the name, the proper name under. If you use under as a single word, maybe under is just a location, like under the table. But if you use under as a proper name, imagine that we did lower casing, so everything is in lowercase. You'd have under does that, so you know that under is the noun of the sentence, the subject. So if we apply the count vectorizer to our sentences, we came out with 4,624 words. Okay, acceptable. What are these words? Well, here in using this method, get features name out of bow vectorizer, basically you have the words, every words correspond to a different column, and they are ordered in an alphabetical order. So as you can see, there are words that are very dummy, not even words like arc, indifferent way to write it. So even if we try to compress the meaning, there can be something useless here. Now, let's do this. Let's count how many times every word appears in the whole corpus, so across all the sentences. We will do by simply summing the results over the column. So we take a column, every column corresponds to a word, summing every value in a column gives us how many times a word has been used in our text. And we start to discover something, I would say boring. What is the most relevant word? Not the most relevant, the most frequent is the word the. What a surprise, right? this is ugly. Maybe we can do it with a bar plot. I just wrote here the code to plot a bar plot. Here we have that the word A appears a lot of time, then you have the word B, what a surprise, the word and, again, not a surprise. Surprisingly, then we have the word Harry. Harry is quite interesting as a word because we are analyzing the book Harry Potter.
Interesting,
Huh?
interesting, you sound. When in Harry Potter book,
You have Harry, like as a...
very surprising.
Not really surprising, right? But I show you that is even more surprising than what we expect.
At least it's content.
Yeah, I mean, at least it matters with the book, right?
Don't make no sense.
But for social scientists, this is not convincing because like this is a lot of effort to reach the point where most of the words are about the being, of course. There's being.
This is the exact point why I don't like.
Harry. Oh, what a discovery.
Yeah, indeed. But in the end, we are pretending to do something very easy. We are just counting the frequency of the word. Now, before continuing, just let me show something else, but then we will return to this exact point. Let's see the representation of the first sentence. Of course, it has a lot of zero because in the first sentence there are not all the 4,000 words in the documents. Let's filter the zero out just to see the words that have been used in the first sentence. And we have this representation. So these numbers are the representation of the first sentence for the computer. And the computer works with numbers. So this is what you provide. You don't provide the context, so you don't know how this word has been used. But for the simplest model we can do, we can just provide this.
So now it's actually looking at the sentence as opposed to the paragraphs.
Sorry, I say sentence, but no, every document it's a paragraph. Yeah,
Okay.
yeah, sorry. So, what bag of words does and what it loses? Yeah, of course it's simple and transparent. Good. It turns text into a numeric representation in a very easy one, so it's good. But we lose information because we lose the order of the word, so the context, we lose the syntax, and we lose the meaning of these words. So this will be a problem also for later. But so the question is, do the most frequent words make sense? Are there garbages in it? Do we need to adjust cleaning rules? We can do a lot of stuff now. Well, inspecting the output is part of the analysis. I know that I'm stressing this thing a lot of time, but it's really, really important. And there are people that provide their homeworks in computer science class, and I know 100% sure that they didn't inspect the results and then they do mistakes. But so, before continuing with something that is more cooler, let's do how to plot this word count in a way that is understandable for human. It's not quantitative, but is a good way to have an exploratory inspection of the results. We do it with word cloud. Word cloud basically is a way in which you plot a figure. I will show you the figure and then I will return on the code. Here you have the most frequent words that are bigger and the less frequent words that are very small. Again, if the representation is boring, the word cloud is boring too. How do I do? I imported the word cloud function, and I prepared a dictionary where this is a very compact syntax to create a dictionary. Basically, here I provide a list of terms. Here I provide a list of counts. I zip them together, and I transform in a dictionary. A dictionary is that. Do you remember what is a dictionary?
Yeah.
It's let's.
Key with a value.
Yeah, key and value. That's it. So we have a dictionary where for every key, that is the sentence, we have the count of every time, how many times it appears in the whole text, in the corpus, across all the paragraphs. So let me repeat. Boring representation, boring word cloud. Why? Well, because this time the size reflects the total frequency of a word. But maybe we want something else, we want to give a weight to this word that represent the importance of this word in the corpus, not only the fact that appears many, many times. Indeed, frequent is different from important, and we discover by looking at the text that frequency actually is not so important. We want importance, not frequency. Indeed, in this representation, the domain specific, meaning the terms that are specifics for Harry Potter book, are hidden in this representation. So now we find a way to measure importance instead of frequency. To do that, we will use TF-IDF. That stands for term frequency / inverse document frequency. First of all, are the most frequent words also the most informative ones? You know the answer. So what we do now is, first of all, to remove stop words. What are stop words? Are that kind of words that appears in every context, so they don't deliver information about the domain-specific text. We will remove them, and while we remove them, these are some examples of stop words. For English, also stop words, of course, are linguistic dependent. So in my cases, I'm working with English, but if you change the language, you need to change also the stop words. And together with removing the stop words, actually there is a function that removes the stop words and does the TF-IDF representation all in once. So this is why I put these two things together. Before doing that, let's have a grasp of the idea that is behind TF-IDF. So, TF-IDF is awaiting schemes, meaning that provides a weight to every word, that combine how many often a word appear in one document and how many times that word appears in that corpus. If a word appears many times in one sentence and then it disappears in all the rest of the documents, probably this is very important word for that specific sentence. The contrary, the word "the", okay, we are going to remove stop words, but this is a good example. It's not informative at all, so we, okay, it appears multiple times in a sentence, but it appears also a lot of time in the document, so we want to penalize this word. I will start with a simple example, okay? We have four sentences. The cat sat on the mat, the dog sat on the mat, the cat chased the mouse, the dog chased the cat. 4 sentences, okay? This is our total number of documents. TF-IDF basically it's just a product, a multiplication between term frequency and inverse document frequency. So it's called TF-IDF because it's really a multiplication between TF and IDF. What is term frequency? Term frequency gives us the importance of the word inside a document. So it's the fraction of time that there is that word in that document. Meaning, the cat sat on the mat if we do the term frequency for the word cat, we have one time the word cat out of 6 words in this first sentence. So its term frequency is 1 out of 6. In the second, I don't know why I have this blue bar here. Just annoying, but I didn't put it. I don't know why it's appearing. Never mind, I will solve it later. In the second sentence, there is not, the word cat appears 0 times, so the term frequency is 0. In the third sentence, it appears 1 out of 5 words, so this is the term frequency of the word cat in the third document. And in the fourth, it appears 1 time out of 5, as in the third. This is the term frequency. We compute them. Now, the second question is the word rare across the corpus? To define rarity, we use inverse document frequency. This is the math behind it, the equation, but it does not really count. Basically, we count this df of w is how many times a document contains that word, okay? So for the word cat, this word appears 3 times out of 4 documents. So this is the inverse document frequency of the word cat, okay? So if a word appears often in one document, we have high term frequency. But to have a high TF-IDF, we want that word appears many times in one document, but few times in the rest of the document. Again, this is the final example. So we multiply the term frequency of the word cat for the inverse document frequency of the word cat across all the document, and we obtain the score for word cat. Okay? Of course, it's very low. It's quite low. Why? Because its cat is very important in the sentence, but is it's not very important, but it appears many times, only once, but many times in a sentence. But it appears also almost in every other sentence, so its weight is lower than, for example, other words like, I don't know, let's take another word. So, what's the intuition? If we use the FIDF in our book, do you have a question?
I tend to disagree with this method. I tend to disagree with this method. The only reason I'm saying is it does not work well with literature. For example, let me give you an example. Let's use the word I. If there is a novel written in the first person, and we're using the word I, so there's a possibility that I will be repeated many times in a novel, and that I person is the most important person in the novel because he is a protagonist. So for me, protagonist or the main character is the I. So in that case, when we will see a high frequency of I in a novel written in the first person, we may assume that I is not important. But if we look back and see and analyze...
Try to look in a different perspective. Is it I important to characterize a specific sentence in a book where I appears in every sentence?
I didn't get the point.
Now, I want different representation of every sentence in order to understand the differences across these sentences. So, if in every sentence I have the word I, okay, because I wrote a book in the first singular person, then its importance is very low because every sentence has the word I. So it's useless to distinguish a sentence from another because every sentence uses the word I. This is the meaning. Instead, if I'm comparing the libraries in a book, no, the books in a libraries, sorry, maybe the I word is very important because it appears many, many times in a book that is written in the first singular person, but does not appear in other books in which they use the third singular person. Okay? And so in that case, I is very important. Do I deliver the message?
Yeah.
Okay, so in our case, for Harry Potter, they see this kind of words, can be almost everywhere, so very low score, very low TF-IDF. The word Ron, that is one of the protagonists, professor, maybe we have these words only in few documents, so the TF-IDF, I expect that is high, okay? But this is just my expectation. Let's see what happens really. So we don't want to have the most frequent. We want to have the most distinctive sentence, the most distinctive words. Again, TF-IDF suffers the same limitation of bag of words, so it ignores the word order, it ignores the context meaning, the context and the meaning of that word, and it treats words independently. So it's just a bag of words, a little bit smarter, but in the end it's the same of a bag of words. So let's do that. To do TF-IDF, I use TF-IDF vectorizer instead of count vectorizer. Very intuitive. I remove stop words in English. If I'm working with other languages, I need to also change the stop words. Here I also set some parameters. I suggest you to set as I do. Basically, from this representation, we want to squeeze, to simplify the things, and so we remove also words that appears more than in the 90% of document, and we remove also words that appears less than 1% of the sentences. Okay, but here there are parameters, you can play with it. If you want all the words, you can just put a 0 here, and you have also the very rare words. However, as I told you, we want something as simpler as possible. So I will remove the two tails of the distribution, the very rare words and the very frequent words. We do TF-IDF. This time we find a very small vocabulary of only 208 words. Don't be scared about that, it's just the 208 most important words in our document, in our book. As before, I can have the most important words, but this time important, not frequent, in the book. Again, we have Harry. So even if Harry appears so many times, so it has a lot of inverse document frequency, still the most important word in the book. What a surprise, we are talking about a Harry Potter book. But you see, you start to appear domain-specific words that actually here are almost only names, like Hagrid, Ron, etc. Now we repeat the word cloud plot, this time providing the importance of the words, not the frequency. And this time we have something more interesting. Is there an example that looks weird to you? I don't see anything weird, but... Yeah, say. Say, it's a verb, so there will be a lot of sentences.
Yeah, so it should not be there. It should have a high idea, or what is it? Low idea or high idea?
It means that is...
It's occurring in many sentences, many documents, and it should have a low one, low input.
Yeah, but
So the word look.
yeah, this means that it appears lot of time, but not in all the sentences. So it's a compromise. I mean, it's if it was more frequent, you would remove it. Instead, it's not so frequent. For example, but I mean, it's not the most important word here. Say has a lower score than Harry, for example. But yeah, I agree. I mean, I don't like to have this kind of verbs, but in the end they are important because in some sentence the meaning is that someone is saying something. In other sentences there is someone that is looking. Okay, so different verbs for different contexts. Let's compare the two word cloud. The one before with the bag of word and the second with the TF-IDF. Well, you see the difference by yourself. Here is boring. Here is less boring, I would say. Please.
I think there is still something like LL and VE, which means have and will, the short form of these words. So we will delete this one.
I see. Like, let me return here. You are saying like LL here, right?
VE.
I can't find it, but I mean,
Between the R and R, between the R and Harry, R and I.
okay, here. It is what it is. I mean, it's if you don't like, you can return to the lemmatization. You can try to preprocess more your text. You can try to remove them. Here, I'm not worried about them because we have just a few of. I mean, they are small enough. But of course, it's a good practice to look at this picture and say, "Oh, have I included some noise, some garbage in my text that I wanted to remove?" And so you return back. It's an iterative procedure. You arrive here, you say something you didn't want, you return back, etc., etc. Okay. I finished this part. In the afternoon, we will start with the methods to extract the information from your text. Okay? We are already extract some information of your text, but maybe this was just trivial. We can extract more information. Now, till lunch, I guess, it would be nice if you can click on this link. This brings you to another notebook in which there are exercises. So, what I ask here is to download the new dataset. In this dataset, I'm providing like around 5,000 comments from Reddit. So we are working with comments. Comments are much more difficult than books because you can find something very unexpected inside them. And the task is to repeat what we already did so far. So in every step, I will describe the task. I will ask you to write your code here. You can copy from the notebook before. I mean, yeah, no, it's a suggestion. You can copy from the tutorial, but because no one writes their code anymore, we just ask ChatGPT, but you are lucky, there is a notebook, a tutorial just for you.
And there's Gemini there.
And there is also Gemini, so, I mean, you can do it. And also, I also provide the solution because I'm let me say a very good teacher. No, I'm joking. No, I also provide the solution because don't check. Try to do by yourself, but if you go home and you didn't finish and you don't know the solution, at least then you can check and see how I will do the task that I ask. So again, just copy this notebook. Don't use this one. This is mine. Okay. And copy this on your Google Drive and start to do that, okay? I'll try to answer your questions when you face problems. Thank you. Questions? I will wait later. Just like a thing. Here, the data set is in a CSV. Maybe you remember that you can read CSV with pandas, that is a specific library to handle CSV. What I did here basically is to ask you to read the CSV. Here there is also this .gz, that means that the file is also compressed. I did that because otherwise we overload the network by only downloading an uncompressed file. So the file will be compressed, but Pandas is able to read also if it's compressed. I extract only the column body that contains the text of the messages. Otherwise, if you want to explore, there are also other columns that deliver other contents if you want to check, but for this exercise you just need the body, so the text of the content, and I transform the column body in a list in which every element is a different document, every document is a comment. And I just took for this exercise the first 10,000 comments, but there are much more in the data set that I provide. Okay. Okay, can you hear me? Well, we will resume now from where we left before doing the exercises. In this afternoon, we will see three methods. In the first one, we use the simple representation of the text, so the TF, IDF that we prepared before. We use this simple representation to extract topics of in the documents we are analyzing. The method that we will use is non-negative matrix factorization. I will explain how it works and why it should work. It's a simple method. With simple, I mean that it works with a simple representation, so with the TF-IDF. And so it's not the state of the art of of the topic modeling, but it has the advantage of working with a simple representation of so it fits well the level of the class, and also it's very interpretable. So for every topic you have a simple way to visualize what are the most important words in every topic and the most important documents in every topic. After that, we will return using the library Spacey, because so far we used Spacey only to do lemmatization, but actually what internally Spacey does is a bit more interesting, because it does part of speech tagging. We will see what it means, what this means. And then in the last part, for the last part, I will probably ask you to have a break, because we are going to transform the words into vectors. Don't be scared, I will explain what does it mean. But for vector representation, the model that we are going to use, it's pretty big. So it asks like 10 minutes to upload it in the on Google Colab. And so maybe there it will be good to have a break, or for the coffee break, or for doing the exercises, and then we will return back to the tutorial. Otherwise, if we run out the time, I will just show you some results that I already computed yesterday evening, and you need to trust me then, and you will try to repeat them when you are at home, just to don't overload the Wi-Fi of the university. So, let's start from the beginning again. Why? Because in this break, it's likely that your Google Colab disconnected, and now you don't have anymore the file here, the one that you uploaded before, the Harry Potter file. So we need to upload it again, and we need to run the notebook from the beginning. Well, now there is this tab that there is this command here that usually is useful, that basically runs all the cell from the beginning to the end of the notebook. Unfortunately, we cannot use it today for a simple reason. Because since Colab provides these resources for free, a lot of people try to exploit these free resources to run their big models, okay? And so if Colab think that you are doing something automatized just to exploit the resources, it disconnects your notebook and you are not able to run it from the beginning to the end. This is also another reason why I usually prefer to work on my notebook locally. So let's start from the beginning. Let's have a bit of patience. Let's read again the file. I don't know what it is. This shouldn't be here. I can't just run everything in a row because otherwise Colab will tell me, no, I disconnect you. Meanwhile, if you have any question about what we did so far, please raise your hand. At least we can use this time while we are waiting. Is it working also for you?
Is it a Reddit file or Harry Potter, right?
Yeah.
Harry Potter.
Yeah, the Harry Potter one. Okay. Tell me when you finish so we can start the next part. Or raise your hand if you didn't finish. Maybe I can try meanwhile to explain the theory, just to give the intuition behind this method. And when I start again with the code, if you didn't finish, please tell me so I can wait, okay? So far, if you remember, we pre-processed the text. We built a representation with TF-IDF, and together with TF-IDF, we came up with a vocabulary. That is the list of words that you are considering in your representation. We reduced this representation, and so we only have 208 words, hypothesizing that the others doesn't matter because or they are too rare or they are too frequent. Now we use a non-negative matrix factorization to discover cluster in your topic, in your documents. With clusters, I mean topics, okay? It's a disclaimer that I already did 5 minutes ago, but I will repeat. NMF, it's not the state of the art. There are better methods to do that, okay? If you are interested in this, ask me later. I will suggest other methods that work better. Otherwise, but to understand these methods, maybe it's useful also the lesson of tomorrow, and it's a bit longer to understand. They work more as a black box, so it's more difficult to understand what it does. Instead, the advantage of NMF is that it works with the TF-IDF that we already did this morning. So it's simple, it's transparent, and the model doesn't use a complex representation of the text that includes the meaning of the words. Of course, if you include the meaning of the words, it will be better, but it will be more complex. So the idea of NMF is that we start by a matrix, the TF-IDF matrix, the matrix A, that have m rows, meaning that you have m documents in your file, in your corpus, in your list of documents, and n columns. N columns corresponding to n words. So it's 208 words for our example. The idea of NMF is a kind of a magical trick in which we factorize the matrix, meaning we break the original matrix in two other matrices, and the product of these two other matrices is quite close to the previous matrix. But we don't need the product, so we don't need to know the algebra there. We just need these two separate matrices because they provide a lot of useful information. The first matrix has m rows as the number of documents and k columns. Let's wait a minute, then I will tell you why there are k columns. There is instead the second, you see this, disconnected the runtime. It means I need to start again from the beginning, maybe. I hope no. I don't know why it appears, but okay, seems that it's working. By the way, so the first matrix, the matrix W, has m rows and k columns, and the second matrix, the H matrix, has k rows and n columns. So here we have m rows as the m documents that we have in our list, and here we have the n columns as the number of words that we were using in TF-IDF. So, what is K? Well, K is a parameter of the model. In machine learning, when you say a parameter of the model, you refer to it as a hyperparameter. So something that you choose for the model, it's not something that the model learns by itself. You just to provide this number to the model. And this K represents the number of topics that you want to identify in your corpus, in your list of documents. So, in this way, W, the first matrix, becomes the feature matrix. Means that for every document, so for a single row of this matrix, you have a score that says, the probability, it's not a real probability, but let me say probability, actually, it's not a probability, it's a score. But basically it says, the probability that the document belongs to the first topic is 0.01. Of the second, it's 0.3. And so you say, okay, 0.3 is higher than 0.01. So it's likely that this document belongs to the second topic instead of the first one. I will show you with an example later. With the coefficient matrix instead is that for every row, for every topic, or given the first row, given the first topic, it gives a score to every word. And the word with the highest score are the most representative for that topic. Okay? So with this simple method, you have a way to know what are the most representative words for every topic that you discover and the most likely topic for every document. So let's import our function.
What is a topic? I just couldn't grasp it.
Okay.
Is it like a theme or something?
A theme, yeah. It's I don't know. Are you reading a paper of astronomy, or are you reading a paper about science, or about computer science, or about social science? No, different themes.
But sometimes within a paper we have different themes. For example, even if it's an astronomy paper, we will have different themes within that paper itself.
Well, here we will discover the macro topics. Maybe if we apply this method to only on paper of astronomy, we will find more detailed themes. Like, why? Because probably every document mentions space, so space becomes not an important word, and so the TF-IDF highlights more other words, and so when you factorize the two matrix, the important words becomes other. If we apply to every abstract of every paper in archive, probably we will identify something that resembles to the main topic, like computer science, social science, others. Okay, so if you are here, everyone is here, I guess so. We choose to search for 5 topics. Okay, this is not something I know. Just I say, okay, let's try 5. Let's fix this hyperparameter. The other two things, the other 2 parameters are not important. Means these random states just fix the variability of your results. It's important to fix because otherwise every time you run the notebook again you will obtain different results. We don't want that because we want to repeat this analysis only once, so we fix the random state. And max iteration is this is an iterative method. The higher this number, the longer the computation, but the more precise. Okay? So let's fit this model on the TF-IDF matrix that we computed before. And in this way we have the two other matrices that I was mentioning before, W and H. Okay, as you can see, the dimensions. Before we have almost 3,000 documents, and here we have 3,000 documents, and we choose 5 topics. Indeed, here we have a 5. Instead, the second matrix have 5 rows as the number of topics that you choose, and 208 columns. That is the number of words that we were using on TF-IDF. Now, it's interesting because we can learn something about this topic. For each topic, we will take the corresponding row in matrix H, in table H. We sort word weights in descending order, meaning from the one that have the highest score to the one that have the lowest score. And we keep only the top, so the words with the highest score. And we use this score to interpret the cluster that we found. To do that, we use the vocabulary extracted with TF-IDF, and this function that is very basic. You provide the matrix H, the vocabulary, the number of the topic from 0 to 4, because remember, you start to count from 0 in Python, and the number of words that you want to show. So 10 words. I can remove this. Okay, the rest it's not important. I'm just going to say that this function will plot a bar plot. So for every topic, I will have a bar plot like this one. And so, first topic, by far the most relevant word is the verb say. In the second, the most relevant word is Harry. Then Ron, Hermione, it's not the right pronunciation, I know, but it's the Italian one. Neville, what is the pronunciation? Hermione, I'm sorry. How you do pronounce? Great.
Actually, harmony. Because harmony means harmony, like the balance. But harmony.
No, but in Turkish. Oh, okay. Okay. No, but not even for Italian, but we pronounce as in a bad way, saying Hermione. It's also in the films, it's in the movies. We call it Hermione, as you read. It's
Is it like that like that on the movie?
Huh?
When you watch it, is it that like that?
Yeah. This is why. So, and topic 3 is Hagrid as dominant word. Topic 4 instead seems a bit more interesting, but it mixes a lot of stuff. So, let me do a disclaimer on the topic quality. First of all, if topics look repetitive or uninteresting, this does not mean that the model is wrong. Simply, in this case, we are using something that is really homogeneous. One book, right, by the same person. So the style is the same, etc., etc. I'm sure that when you will use this on Reddit, you will find something more interesting. Second, we can adjust K, the hyperparameter, the number of topics, which if K is too small, topics tend to be very generic, meaning you can't infer the real topic inside a cluster. You seem like the topic 4 seems to mix a lot of stuff, and you can't detect anything emerging. If K is too large, instead, with the right K, topics may become more specific. When K is too large, topics becomes repetitive or fragmented. So you have more topics that in the end means the same stuff. Exploring different values of K help us understanding the structure and the limits of the corpus that we are analyzing. So for example, the fact that the topics are so let's say, boring, I would say, because just one word dominates. And so if I analyze topic 1, it's probably all the sentences that mention Harry. But of course, I mean, we are analyzing a single book. If we had more dishomogeneous corpus, we would have more interesting topics. However, let's try to adjust this K. I wanted to try 10 because I tried at home. Now you have 10 topics here. You can recognize by the matrix. Let's plot them. Even in this case, the topics will not be super interesting, but at least we have something more interesting. Like here, topic 8 seems to mention Dumbledore but most important, Professor McGonagall. The topic 7 seems to mention the first part of the book with the uncles of Harry, so Uncle Vernon, Aunt Petunia, etc. The others, instead, we can infer that there are two kinds of topics. The topic in which the protagonist dominate the topic, so this topic 1 is all the topics with in which Harry is the protagonist of the sentence, or at least there is Harry in the sentence. Other topics, instead, the verb dominates. So we have a topic in which there are all the paragraphs in which someone is saying something. We have here a topic where there are all the paragraphs in which someone knows something or someone look something. Okay, there is something. We did the first step, but this is not satisfactory. So let's continue. Now, let's look at the other matrix, W. The matrix W, as I was mentioning before, I need to reduce the size, okay, has a number of rows that stands for the number of documents that you are analyzing, and a number of columns that stands for the number of topics you are trying to discover. Now, with this you can do interesting stuff. First of all, given a row, you can take the column with the highest value and say, like in this example, the first document, document 1, belongs to topic 3 because 0.4 is higher than the other two. Okay? This operation, it's called hard clustering. Means that you assign every document to a single topic. It's good because at least you can, for example, count how many topics that there are in your, how many documents there are for every topic. But sometimes, I'm sure that you are thinking that a paragraph can belongs to more than one topic. Well, both the things are true. If you allow that a document stands in more than one topic, you are doing soft clustering, so there is not a separation across clusters, but you are saying a document can stay in the overlap across two topics. Let's visualize the matrix. Of course, if I look in this way, I can't understand anything. I can zoom a little bit now. But with this argmax function, I'm saying for every line, this is a line, so this is the first document in our collection. Let's keep the column with the highest coefficient, with the highest score. So the first document belongs to cluster 0, the second document belongs to cluster 7, and so on. In this way, I repeated what I did before, but this time I assigned it to a variable. I can plot the topic distribution, meaning how many documents there are in every topic. Okay? Now, another thing that we can do with the matrix W is that if instead of looking at the rows, we look at the columns, the highest scores represent the most representative topic for that, represent the most representative documents for that topic. Why we need that? Because to understand what a topic is about, we print the most representative document and at least we figure out what this topic is about. Okay? Is it science or is it, I don't know, astronomy or computer science or whatever? Okay. Tell me if I confused you or if I give an intuition. I mean, what's the balance? 50-50? 80% confusing? Can we continue? If you want, I can stop here and we can talk. So it's a good point to ask question now. Okay, so let's try to use this theory, this intuition that we had. Let's try to use them. So with this function, we get the top words for every topic, as we did before for the bar plot. With this second function, we have the indices, so the position in the list of the top documents for every topic. Finally, with this function, we put things together, and so we print the topic ID, the most important words for the topic, and the most important documents for the topic. Let's do it. There is a mistake. I didn't run this cell before, sorry. Okay, and now you can analyze what we obtained. And if you are following on your notebook, I will not scroll down. Tell me there is a mistake here. And I will zoom out a little bit. Try to find the mistake. There is for sure at least a mistake. Then probably there are also others. Scroll the topics. For every topic, take the top words and take the top documents and tell me where you see a mistake. Oh, also an important thing. Here, when I print, I'm using the original sentences, not the one that we manipulated with lemmatization, etc. Not because I'm providing to the model that original sentences. I'm providing to the model the simple sentences. I provide the TF IDF of that sentences. The model never saw the exact sentences. But for us, the original sentences are clearer, so we use them to understand what the topic is about. By the way, someone have a guess? Look at topic 9. Where is the error? Yes? No guesses? Well, it's the same sentence. It's not even a sentence about the book. It's just the markdown of the book. Yeah, the title of the page, the top markdown of the page. No, you know, when you read the book, probably on the top right corner there is the name of the book or the name of the chapter. Where this is what happened. I didn't recognize it at the beginning, so now it's there. it's a mistake that emerged. With manual exploration, I didn't see it. Now that we know, we can return back. We can filter that sentences from the list of sentences that we want to analyze. We repeat the FIDF, and we repeat the topic detection. I will not do that now, just to don't mix stuff and create confusion going up and down to the notebook. But basically, it's just if you decomment this, if you decomment this notebook, this cell here, you basically, I'm basically filtering all the sentences like this one because they are clearly mistakes. And the topic detection allow us to discover these mistakes that can be in your text. I mean, it's normal to have mistakes. The things is that you don't be worried about that. It's an iterative process. So you find the mistakes, you correct, and you restart from the beginning. And you continue this loop till you are not satisfied enough. Okay? Okay. I will not do now, just because we saw that the topics are not so interesting in a Harry Potter book. But I want to now go to a second part, in which we try to characterize more the linguistic pattern inside each topic. Because even if we don't provide a context to the model, still the topics can differ based on the verbs that they used, the protagonist in the sentences, etc., etc. To do that, we will use again the spicy library, doing a kind of linguistic analysis. It will not be perfect, but is good enough to try to represent, to try to distinguish our documents. So basically, what Spacy does when we do lemmatization is, first of all, a tokenization. We will see what it means. And then a part of speech tagging. Part of speech tagging is very intuitive. Given a sentence, every word it's the part of the speech, and we can provide if it's the model tell us if that one is a verb or if it's a noun, a proper noun, an adjective, an adverb, etc., etc. Okay? Now, for if we do that on a lemmatized text, we already provide some documents that have a very simple information in it. So we want, for this step here, we want to do a step behind. So returning to the lowering to the clean sentence without URL and tags, but having the one with marks, for example, with point, punctuation, etc. When we call the method NLP on a text, okay, that is the thing that we did before when we were doing lemmatization, Spacy does tokenization, part of speech, and lemmatization. We'll only use the lemmatization, but there are the other two important things that are for free. First of all, what is a token? Let's say that the token is the brick of the smallest unit in your sentence. It's not something that comes from linguistic. It's something that the model, when we train a big model, the model try to find these minimum units inside this inside a sentence. So depending on the tokenizer so the model that we are using, or better, the tokenizer of the model that we are using, a token can be a word, an entire word, or a part of a word, but it's a token also a number, a punctuation mark, special symbols, everything has their own token. For example, the example don't worry, some tokenizer can break it in the token do, that is a verb. This token here, that has no meaning in linguistics, but for model problem probably it means the negation. Worry, it's a word, and the exclamation mark. Why tokenizer matters? When we apply this model, we don't see the tokenization. So why I'm losing your time by explaining tokenization? Because it's interesting to know that tokens are what the model see and what the model understand. And basically different tokens count the same for the model. And it's how the model represent internally the text. So when we say that the model understands the text, means that someone trained that model to do this tokenization. These tokens means something for the model, and when the model finds in the text, says, okay, I know the meaning of this token.
So this is how it works for English?
Yeah, but also for other languages. Yeah, yeah.
Is there a convention on how tokens are?
No, because we don't guide the model in the way in which it finds the token. It's just, it sees all the Wikipedia pages, it trains with all the Wikipedia pages, so it finds patterns in these texts automatically, without that anyone tell him probably what to do. Okay, so this was a digression on tokenization, but you can even forget about tokenization. Let's talk about part of speech tagging, where part of speech is basically a tag that, so a label that the model gives to every token that is a compute word. So it does not give a tag to the punctuation or to the spaces, for example. Example of post tags are nouns, verbs, adjective, proper nouns, adverbs, etc. Those are useful because they add grammatical structure to the text, and it's also the way in which the model starts to understand, interpret, and putting the words in relation when it does the magic. They allow us to distinguish between different roles of the words, so I can use the same words in different roles. We move beyond the simple word count, so we discover these topics using basically word count, more refined with the FIDF, but it's always word count. And we start to provide more characterization for our topic. For example, I may heard before that some of you is doing a project about how different media talks about the same topic. Well, this is something that you can use to see how the same words are used in the different contexts. So, let's load again Spacey. As I was saying before, post-tagging works best on minimal processed text. So we will do it on the original sentences, even if we use the lemmatized sentences to identify the topics. It will require a bit. Oh, also, before I used NLP for every single text, and it was a bit slower. Instead, this time I can use a dot pipe and provide the whole list of sentences. This is much faster. It's basically parallelized internally. We don't know how it works, but it's faster. So now, what we do with this part? Well, we take the top n words, as we already did for using NMF for every cluster. We print the most representative documents, so as we already did in the previous block. And we also plot the distribution of the top noun, the top verbs, the top proper nouns, and the top adjective inside every topic. This helps us again to provide context of our topics, because topics is something that are extracted in an unsupervised way, so you don't know what they are really about. You need to start to extract information to understand why a topic is different from another one. So here I defined basically a function that given the indices that we need to analyze and the documents, the entire list of documents, it basically counts the part of speech, the tags that we are interested in. In my example, I will be interested in noun, proper names, verbs, and adjectives. Here, in this function, if a token is a punct or is a space, I just jump it because it's not interesting for me. Okay. Here, this other function just plot the distribution in 4 subplots. Yeah.
Can we understand the subjects of the verbs, the actors of the verbs that we distinguish? I mean, are you including subjects into the noun?
Yeah, but can be, I mean, actually no, the answer is no. We can't know if the noun is the subject or other parts.
There are models to do that.
Yeah.
I'm not seeing it there, but you can find it.
Yeah, this is an important recommendation. It's here I'm using this one because it's easy. But if you're interested in understanding, for example, who is the subject, etc., you can find different models for different languages. Do you have an example?
It was named
Name
Name identity recognition. Yeah, this is the task. Yeah, you're right. Okay. So let's do that. It's almost like before, but now for every topic you have also the most important noun, the most important verb, etc., etc. That's it. I'm curious to know what happens with the Reddit dataset or with another dataset that you are using now, because I didn't try to do that, because I want to be surprised. But this is what happens with Harry Potter. You see, there are mistakes. Of course, there are mistakes. For example, the fact that we are using, since I use the lowercase of the sentences, Hagrid is also at the top of the proper name and of the noun in our so sometimes the model recognizes Hagrid as a noun, sometimes as a proper name. So there are mistakes. It's not perfect, but it's just to understand what the topic is about. Now, I'd like to start with this part, but this is the part in which I need 10 minutes to upload the model, okay? So I would prefer to show you the results that I already computed. Then maybe we will have, we will do the exercises, and then we will return back here to finish this notebook, okay? Once we have enough time to upload the model. I'm sorry, this part can't be really interactive as before, but just because this model takes 10 minutes to upload, and every time the runtime is disconnected, I need to upload again the model. So, I think this is the most beautiful part of natural language processing, and this is the part that makes me say, okay, this is magic. We will see a part, we will see whatever it was before 2017. From 2017, transformers, I will tell you at the end what they are, arrived, and they literally changed the world, probably. So, until now, we represent text by counting words. This works surprisingly well for a lot of topics, for a lot of analysis, especially when the corpus is very dishomogeneous, with a lot of topics in it. But it has an important limitation. Words are treated as independent labels. So there are no meaning in the words that we are using. We are not saying the model what these words means. So when we do TF-IDF, the word sorcerer and the word witch are as different as sorcerer and table. But of course, sorcerer and witch seems to be more semantically related than sorcerer and table. Do you agree with me? Yes. Well, actually, with TF-IDF, the model does not know that. And so, sorcerer, if you try to encode with a bag of words a sentence in which there is only the word which, we have something like that. Then if we try to encode the word sorcerer, we have something like that. Table, something like that. The model ingests everything, don't ask questions, but actually they can do much better than this. Indeed, what if we provide the meaning of the word to the model? How to do that? As we said before, the computers that does not work with words, with the text, they work with numbers. And so we will use numbers too. Basically, for every word, we will, instead of using every word as a label, we give each word a position in a space. What does it mean? That we transform the words in a series of numbers. This series of numbers are the coordinates, like the geographical coordinates of these words in a space. And these positions reflect how close two words are. The 2-dimensional example is that here we have king, man, woman, something related to human, so they are close together in the space. We have apple, banana, and orange. They are fruit, so they are close in the space and distant from the previous one. And then we have football, golf, and tennis, and they stay in another part of the space. This is a 2-dimensional space, so the space to put the words is limited. But this is only an example. When we do this, nowadays we use, with fast text, the model that I wanted to use today, we use 300 dimension. Of course, we can't plot 200 dimension, but the model try to learn, when they train this model, the model trying to learn this list of numbers. We call them vectors. Don't be scared about the word. And there is a lot of magic here, because each word is a vector, a list of numbers representing its coordinate. Similar words are words that are close to each other in this space with 300 dimensions. So the meaning of the words become distant. The more distant, the more different in the meaning. This type of representation is called word embedding, okay? And the cool part about it is that we don't know how the models learn the embedding, but if you are curious, this is a good quality, so check for it. You just need to know how to use them. Good news. You have a question? Yeah.
Let's say, for example, if I have a word sound, it is two different meanings. One, like sound means like good, another sound means
This is a very good question.
so.
I will answer in the end of this notebook.
We can read the question.
What if there is polysemy, meaning the same word means two different things?
Okay.
This is a very good question. This is why you need the lesson of tomorrow, by the way. Well, the good news so far is that we can use pre-trained models, means models that someone else trained. They trained on a million of text, like a small model can be trained on the whole Wikipedia database. Can you imagine to read all the database, all the Wikipedia database? They do. It takes days or weeks of computation. We don't care because big tech are training them and we just use the open source model for free. We will not do that. We use these pre-trained models that are trained by others, by large corpora, and are freely available. This is a taste of what is transfer learning. We can transfer the learning that someone already taught to the model in our context. Recalling a question that arrived the first day, that was, what if my specific domain is a bit different from the one that they used to train? Well, actually, there are techniques that we can't see in this course because it's just an introductory course, maybe an advantage one, that allow us to, it's called fine-tune the models, means to take the models that are already pre-trained and to adapt a little bit to our context. We can't do that, unfortunately, but I think it's fair to say that we don't need now. We will use fast text with these two commands here. This is the part that takes 10 minutes to run, so I will not run. And so I will show you some results. I really hope that if you will try this later, when you have 10 minutes to wait, you can try to play a little bit with that, because I mean, the results they are amazing for me. So, don't spoil the results. What are the most similar words to the word wizard? What is close?
Sorcerer.
Sorcerer, of course.
Witch.
Magic, maybe? Yeah, indeed. If we take the word wizard and the top 20 words, so the top 20 words that are closest in the space, we find all the variation of wizard, of course, but also magician, magic, sorcerer, warlock, mage, witcher, goblin, why not? And then they are on the same book. So we see words like witch, sorcerer, magic. And the important point is that we never try to explain to the model what is a witch and what is a sorcerer, what these words means. It learned it by reading languages. Okay, he read a lot of text and he start to understand what are the meanings. Now, it works also for something else related to Harry Potter word, like the word Hogwarts, that is not even a word, it's the name of a castle. Still, we can see something closer, like Dumbledore, the president. Wizarding, I guess the word. If we have the word wand, we find again something close to magic, etc. Okay, sorry, it's a bit repetitive, but I think it conveyed the result. But now,
Jordan,
yeah,
if you figure out there is a very unrelated word somehow, like hand, let's say, can you interfere here and say to the model, no, this is unrelated? I mean, I know we can drop, but if we drop, then all the sentences would be done. I don't know how we can...
Is there unrelated? Do you feel that and is unrelated with wand? Wand is the wood stick, no?
Yes, I mean, it's just an example. Let's say...
Yeah. No, but it's a... No, actually it's a good example. Let's say that in some context they can be related. So the model understands, let's say the statistical meaning means read a lot of text and tells you the words that are related in a statistical way, meaning that a lot of times are related. Maybe in our specific context they are not related. We can fine-tune our model to so if in our corpus these words are not related, maybe it changes a little bit the position of the words in the space, and so one and becomes more distant. Otherwise, no, actually we can't just drop them. We can do fine-tuning, or we can accept that they can be close even if they are not close in our example, okay?
Of course, we're talking about the text here.
Yeah.
Now we have, they're close in this text.
Here, not. I didn't train this model. Someone else trained. So they are close.
But we're talking about the words that we are finding in Harry Potter's text. That's what.
Yeah, I did only examples that are related to Harry Potter, but it's just a choice. I could choose every word I want. I mean, there are tons of words. I don't know what's the question, actually. I'm sorry.
The question is that we are analyzing words and the meanings, but these words, they are attached to the source which we are working on, which is Harry Potter and the Sorcerer.
Yeah, I choose these examples because of they were related to the Harry Potter world. Maybe it's not the best choice. I mean, yeah, we can also try to do that for random words. Like in the next example, we will see the word king. Okay, let me do the next example. Here I wanted to show you that is something related to Harry Potter, but it's just examples. I mean, I choose manually the words. Yeah.
The question I think is about whether this model was developed based on Harry Potter text or this.
No, not at all. This, I don't specifically remember how do they train this model, but it seems to me that it reads like at least the whole Wikipedia for all the languages in Wikipedia, and probably also something else. So the context of Harry Potter is just my choice. It's the model is generic.
The thing is that my question is about, we are using, of course, a model that had been trained on other content.
Yeah.
I'm aware of that.
Yeah. Okay.
But now we bring in that trained model to analyze the text we have in front of us.
Yeah.
Not yet? Not yet. Oh, okay. So what do these words mean? They're just universes of,
Yes. Let's try another word.
I know because I didn't upload fast text.
But the distances that you see there, it's the idea that the model has of how these words are organized in the English.
In the language.
In the whole
I
English
see.
language.
Okay.
So now he's using the word wizard and blah blah blah, but he could say sun, and sun would be close to stars, to moon, to sky, to something like that. But that's how the whole world is represented through language according to this model. What this model thinks the world is, how this thing.
We could, very briefly, Jordan, we could, however, train a model from scratch. Let's say we could, technically, only based on Harry Potter text, for example.
Yeah.
Then it might have a slightly different idea of what wizard is in that particular world only.
Yeah.
Okay. But this is just a general model trained on tons of English text, and that's what it thinks the word wizard relates to.
Because also it matters the relevance. I mean, I'm bringing a model trained on Wikipedia to analyze contemporary words, but I'm analyzing something that is old. Or I'm analyzing another field which is like more political with another set of, you know, symbolic composition. So how relevant would that be? And also I'm thinking about all the, didn't even deal with the stereotypes, with the biases, etc.
This is full of biases, by the way.
There is a field of machine learning that's trying to deal with this, and you can find models that have been tweaked in such a way as to either reduce biases or to work with ancient texts. So if you think, like for instance, there is one that it's been trained on the Bible in I think it's like 15 languages. So for instance, you can see that the word God in Italian is very close to the word God in some other language, and you can use that for translation, for instance. Okay, so
yeah, I'm thinking also of translation.
No, but this is a very interesting point because it opens two remarks to do, two disclaimers actually. The first one is that if we train the model to all the text that the human knows, the model will learn the biases of our languages.
Yes.
Okay? And it's difficult to remove biases from the model. We can't pretend that the models try to mimic what we already do. So if we are biased, also the model will be biased. And it's difficult to remove biases from the models, like to have models that are fairer than the human being. Okay? And it's a part of the research. I mean, like, I think, I know, for example, that Roberta Sinatra from Copenhagen University works on fair algorithms, how to provide fairness inside the models.
I'm raising this because also in our university this is very important.
Yeah, I see.
Our motto is independent, you know, thought and independent thinking. So we're very much aware of issues of epistemological, you know, fairness, and it is very important for us.
No, this is a very interesting point, and thank you for mentioning it. And I wanted to mention also another thing. Is that, yeah, of course, sometimes you can't really transfer the context, because if I train on documents of 2025 and I try to use them for documents of 1,000 years ago, this doesn't work. You need to or to retrain your own model or to fine-tune the one that are already trained. Usually we do fine-tuning because we don't have the resources to train a new model, because it's...
And since you're mentioning training your model, this is repetitive, so how do you do that? Like if I want to train my model to, you know, in some type of philosophy, for example, and then would I feed it all the books of that writer, for example?
Somehow, yeah. Yeah, like for a project when I was the master, I did a model that like basically speak like Dante Alighieri, as in the Divine Comedy. Okay, I gave all the writing of Dante Alighieri to a model. I trained the model. It's not easy. We can't do that, of course, now, because I mean the course was like 60 hours of machine learning and of lessons. So, but it's a very advanced topics. But you can do that.
So unless it's very like specific to one specific author, it's very niche or very cultural specific, you can find someone else that did something else, or maybe already published it. That's very frequent. Computer scientists like to share stuff, so it's very likely that you will find it.
That's true. Okay, so you say, Giordano, you lose half an hour talking about word vectors, and in the end you are just saying that close words have similar meaning. No, I want to add something else. And it's also that we are not only embedding the meaning of the word, but also the relation across these words. And this really blew my mind every time. So, these embeddings don't just tell us that words are similar, but also capture the relations between words. This means that we can do simple arithmetic with words, like this equation: king minus man plus woman equal to queen. Does it make any sense? Probably no. I hope so. Okay. Well, actually, I'm showing here that this is what you obtain. This is a very famous example. So if we sum the vector king with the vector woman and we subtract the vector man and we take the top one closest word, we obtain queen. So it worked. What does it mean? Well, we are not really doing arithmetic saying that we do 7 minus 3, okay? It's not like that. But we can think it in this way. Each word is represented by many numbers. These numbers encode how the word is used in the language, the direction in the space from a word to another somehow encode the relationship between words. So this means that, what this means, the king minus man plus woman equal to queen. It means that the difference between king and queen, so this relationship here, probably king and queen are used many times in the same context. But what is the main difference? The gender. But this relationship of the gender, the model saw this difference in tons of other examples, like male, female, man, woman, uncle, aunt, king, queen, also in this example. So we are saying, from the word king, let's remove the component that characterizes of being a male. Let's add the word woman, that means add the female component. And what we have, it's actually queen. Okay, this is not just a trick. Okay, this is not just to impress people. It's interesting because these rules are not programmed. No one teaches to this model to do that. It's just unsupervised, let's say. It's the model learned because it reads so many texts, all the English texts that we could provide. No dictionary were used. The model discovered this pattern by itself. So why this is not a parlor trick? Because it shows that the models have in the encoding of the words, they also embed the social categories, the roles, the power relations, and they are already in these embeddings of these words. So again, if we are biased in our language, the model will be biased as well. There is no way we can exit this. So word embeddings learn regularity for social meaning directly from text. I did something similar like, no, this is okay, yeah, this is the example I wanted to do. I took the word Hogwarts. Let's remove school students from Hogwarts. Let's add a prison. And we came up with Azkaban, of course. I mean, yeah, I mean, of course I needed to try several attempts before I came into Azkaban. It's not as beautiful as the other, but it worked. Now, a cool thing is that we can also visualize somehow these categories of the words. Of course, not in a 300-dimensional spaces. We need to reduce to a 2-dimensional space. To do that, we use a model that is I use TSNE here. Just trust the process. I mean, it's too difficult to understand how this works, but basically it takes a space, it starts to stretch and project just to have all the complexity of 300, to simplify the complexity of 300 dimensions inside 2 dimensions. So it works somehow. And this is cool because if I provide some words, again, it's an example about Harry Potter, I'm sorry, I'm a huge fan. You have the authors, not the authors, the protagonists like Harry, Hermione, Ron. You have locations like Hogwarts, Azkaban. You have, how is it called? Magical tools, thank you. Well, then those words are represented in 300-dimensional spaces. With these methods, I compress everything in a 2-dimensional space. I can plot the 2-dimensional spaces, so I can visualize, and that's the magic. We have that Azkaban and Hogwarts are close in the space. The magical objects are here. The protagonists of Harry Potter are here. This is pure magic for me, by the way. I mean, even if I understand how it works inside, this is just magic. I don't know how we realized we could do that. Okay.
So what does it tell us? The clustering of these things in a particular space.
This is the moment in which you should just say, wow. I'm telling you that you can do stuff with these words, okay? And now I will show you how you can use them in a small example. But for today, it's preliminary to use this kind of context. You will use tomorrow, okay? But I will show you something you can do right now. So once you have a sentence, we can provide embedding for every sentence, and then we can do like an average across all the dimensions of the words in the same sentence. In this way, instead of encoding a single sentence, we are encoding also, instead of encoding a word, we will try to encode a sentence, okay? So the encoding of the sentence should somehow capture the essence of the sentence itself. How we can use it in our experiments? Tomorrow you will see something more better, but this is just the beginning. So here I have 2 sentences that somehow related to Harry Potter books, and here I extracted these 2 sentences from an encyclopedia. Okay, so they are just a definition, by the way. Well, if I use cosine similarity, that is a matrix that computer scientists use to measure distances across vectors, let's say. If you are interested in what it is more deeply, ask me later. We don't mind now to understand what is cosine similarity. So basically, by doing the cosine similarity of the average embedding inside these sentences here, we see that sentences related to the Harry Potter word are very close in the space. Sentences that are related to each other, not because they contain the same words, but they are from the same encyclopedia, are close in the space. So even this is already encoded in the word embedding. Finally, I hope this will be really surprising for you. I can't show you the results, maybe I will show you later. Is that you can do also semantic query on your text. Meaning, imagine that I have some words, like some words representing the physical effort, like sweat, head, exhaustion, effort, okay? Let's do an average of these words to have something that we want to recover all that sentences that are somehow related to the physical effort, okay? So being tired, being exhausted, being sweat, etc., etc. I can't show you because this didn't work yesterday, but I will show you later. By the way, by doing this simple operation, so by defining 4 words to define a concept, by doing an average of this embedding, and then by comparing this average, that is the query vector, with the average embedding of every paragraph in Harry Potter, we can take the top closest sentences to extract all the sentences, not all the sentences, but the sentences that mostly reflect this sense of physical effort. Okay? And so, actually you can do it also on what you want to study. Okay? Imagine you have different you have a lot of text and you want to find all that words, all that sentences that express I don't know, desperation, for example, I don't know, anger, for example, yeah, this kind of thing. You define a list of words, here the more the better, a list of words that somehow are related to the concept that you want to express. You do the average embedding of this word. The average embedding of these words is somehow the average meaning of this word. Indeed, I did sweat, that is something physical, with exhaustion, this is something, I mean, you feel the effort, but the sweat is something you can touch. So you have somehow a general meaning. And with this embedding, you try to find the sentences that are closer in this embedding space. With anger, you can do something similar, and you have the comments, for example, on social networks that most express of being angry.
So in that case, if we're researching emotions, for example, within the comments, should we list the emotions as you did?
It's a way to do that. There are actually models that already does that. Okay. So my recommendation is actually to choose a better model, but you can do also with what we learned so far. One important limitation, and this is the last part. Then we will restart with the exercises. This came to your question, okay? For each word, we have a single meaning here. This creates a problem when a single word means multiple things. For example, apple can be a fruit, but can be also a name of a famous big tech brand, okay? So the embedding of these words, of the word apple, somehow reflect both the context, both the big tech and the fruit, in a way that is balanced by how many times you use the word apple as a fruit and how many times you use the word apple as a brand name. But in the end, it's all encoded in the same vector. And this is a problem because the model used the same embedding to express two meanings that are completely different. What we can do, I mean, in social science, context is everything, as far as I understand for your question. So state, party, bank, apple has a meaning in their context. They doesn't have a meaning in general. They have a meaning in the context. So change the meaning they change the meaning depending on how they are used. And to capture this, we need models that somehow look at the whole sentence, that represent the words in the context in which they are. To solve this problem, in computer scientists tried to do some attempts before, but the real things that probably changed the world the most is when this family of models called the transformers. The key idea is that a word depends on the other words that are in the sentence. And so the model applies something that is called attention mechanism to not capture only the sentence, but also not only the word, but also the other words that are related to the word that I'm using. And in this way, transformers can have different embeddings, different representation from the same word, depending on the context. This idea is the brick behind that this idea is then pushed further by large language model, in which we use tons of transformers. And so what I want to deliver is that this model does not focus on single words, but on language in context. And so we will see it tomorrow, because for today it's enough, okay? Thank you. Now, if I'm here to answer all the questions, meanwhile, you can continue with the second part of the exercises. This time, I tried to don't follow a workflow, so I will just leave you the space to freestyle, means to do a free exploration of your corpus. If you are using Reddit, it's fine. If you are, I encourage you to also use different data sets. I think that I would like you do is to identify topics in the documents with NMF. Probably with Reddit, I expect more interesting topics that with Harry Potter. Then I would like that you characterize them by finding the most important word and for each topic and the most relevant documents for each topic. I would like that you do post-tagging inside each topic, and also a TF-IDF and then a word cloud for every topic, because plotting different word cloud would help you to understand what the topic is about, and also it's approved to show that this topic is different from the other, and so word cloud combined with the post tagging, etc., all provide characterization of your topics. Finally, if you have time, try to search on Hugging Face for other models that would be useful for studying whatever you like on these comments or whatever you like on your documents. So, sentiment, toxicity, etc., etc. Don't be afraid if you don't understand them today or if you don't find them today. Tomorrow the lesson will be specifically on what you can find on Hugging Face, actually. So on models that you can use for free. And so let's be creative. Thank you.